Thank you very much for the kind introduction. My name is Monika Duda. I am happy to present to you today my colleagues' research on heat-treated steel under mixed mode loading, fatigue mixed mode loading. So first of all, the motivation to this research is actually working on the microstructural aspects on the fatigue behavior of the material, as well as a fatigue failure that occurs in real constructions due to material degradation and incorrect heat treatment. The material selection criteria were two main, that were heat treatability and applicability in real objects that actually operate under mixed mode load. And this is where the decision was set on material 42CrMo4. There were conducted 3 heat treatments, each representative for different microstructure and different mechanical properties. HT2, which is first heat treatment, was conducted in order to receive structure resembling shock temperature, material after shock temperatures. Actually, the third heat treatment is actually material quenching and tempering, though low temperature tempering that's like still makes the internal stresses a bit released. Nevertheless, the hardness of the material remains similar to the hardened material. And the fourth heat treatment was actually quite experimental. It was conducted in order to receive pure martensitic structure with tiny grains that we could gain quite hard, nevertheless, pure martensitic structure with relative plastic properties. Regarding the mechanical properties as presented in the tables, there are differences, not necessarily very huge ones. What is important to notice is actually the hardness of the material. After conducted heat treatment, we actually focused on the fatigue tests on mode 1+2. To this test, we actually used the CTS specimen sample type that was proposed earlier on by Mr. Ricard. On the right-hand side, you have described the test stand actually and how we measured the visual expression, how we measured the crack length, crack growth, and how we observed its development. Initially, there was conducted a pre-crack under experimentally derived conditions that actually allows us to achieve a pre-crack of around 2 millimeters long. Later on, there was conducted the exact fatigue mixed mode test. First result that I would like to show you is actually a simple influence of the fatigue crack length. As you can see on both charts, you can see the crack lengths in a function of number of cycles for both 30 and 60 degrees. What is expected and visible in this chart, you can see that actually for the 60 degrees loading angle, the life cycle of the sample is longer. It is most visible for the third heat treatment. What is worth noticing that actually the experimental heat treatment, so HT4, which is marked here in gray color, actually didn't change much, which actually points to really nice continuation of the research, basically. In order to receive charts based on the on the SIF function, actually stress intensity factor, we conducted the modeling, and in the middle of this slide, you have the presented model of geometrical feature of the sample, of CTS sample, and how it was actually, you might say, like boundary conditioned in Abacus, which we used actually for modeling. Below the sample, you can see the formulas that actually represents actual force distribution in the sample during the test. In order to receive K1 and K2 values, there was conducted numerical analysis based on what you actually see in the middle of the slides and on the contours integral method, which focuses on the small jumps of the crack length, like close to the crack tip, and basically the visual of this method you have presented on the right-hand side. Based on actual, like physical and numerical tests, there were created charts for K1 and K2 influence and the crack growth rate for all three heat treatments. As you can see in this case, there are no, for the loading angle 30 degrees, there is no visual difference, but when we go to the loading angle 60 degrees, you can actually see that HT4 heat treatment has noticeably lower crack growth speed. In the next step, based on the MTS criteria, we actually tried to present the results in the more unified way using the delta K equivalent. And as you can see in cases of HT3 and HT4, it is predictable results where for 60 degrees you have actually higher speed than for the 30 degrees loading angle. Nevertheless, in the case of the HT2, it is noticeable that MTS criteria seems to have an application. Regarding the crack path,
Monika, you are consuming all your time. Please
I'm
go
sorry.
to the,
Okay, so
go
here,
to the conclusion.
so just quickly here you can see that actually for most of the cases, MTS criterion is fulfilled. Let me skip through the SEM samples, and in the conclusions, I can simply say that according to mode 1+2, the fatigue crack growth for the crack inclinations 30 and 60 degrees was observed only in the initial stage. For the mixed mode 1+2, each time the value of parameter delta K for mode 1 was higher than for mode 2. Fatigue lifetime generally increases with loading angle. Fatigue cracks obtained for mode 1+2 follows MTS criterion with one exception, which is a sample after HT2 under load angle 30 degrees, as well as I can say that based on Huber-Misses criterion, delta equivalent does consolidate all modes. Sorry, one mode actually into one line, which is unusual. And it is actually for the sample HT2 does not consolidate all modes, but HT2 sample is actually quite an unusual example. Thank you very much, and sorry for consuming too much time.